May 2024. A Boeing 777 is cruising 37,000 feet over Myanmar when the force holding everyone to the floor flips negative, -1.5 in 0.6 of a second. Everything not strapped down leaves the floor. 79 people are hurt. One passenger doesn't survive the flight. And yet the airplane itself is fine. It flies on and lands safely. Because the deadliest turbulence event in years never came close to what that airframe was built to take. So, can turbulence actually bring down a plane? The answer lives inside a brutal test, where engineers bend a brand new wing higher and higher until it explodes. By the end, you'll know exactly how much the sky can throw at a wing, how much a wing can take, and why the real danger in turbulence was never the airplane. Start with what turbulence actually is, because it isn't the airplane malfunctioning. It's the sky itself, moving. An airliner doesn't fly through empty stillness. It rides a moving ocean of air, an ocean with currents, waves, and rapids. The fastest currents are the jet streams, rivers of wind at cruising altitude, often blowing at more than 100 miles an hour. Where fast air slides past slow air, the boundary rolls up into swirls, eddies, like the whorls spinning off a canoe paddle. And eddies breed. Big swirls spawn smaller swirls, which spawn smaller ones still, handing their energy down the chain until friction finally eats it. A scientist named Lewis Fry Richardson wrote it as a poem a century ago. Big whirls have little whirls that feed on their velocity, and little whirls have lesser whirls, and so on to viscosity. Fly hundreds of tons of machine through that churn, and it gets stirred. That's all turbulence is, the texture of the sky. Turbulence comes in flavors, and pilots treat them very differently. Storm turbulence, the violent updrafts and downdrafts inside and around thunderstorms. Powerful, but it lights up on weather radar and crews route around it. Mountain turbulence, wind forced over a range piles into giant, invisible waves downwind with rolling rotors underneath. Forecastable and charted. And then there's the one pilots respect most, clear air turbulence, born in the wind shear at the edges of the jet stream. It isn't the most violent kind. It's the least visible. Weather radar works by bouncing off water, rain, hail, ice. Clear air turbulence lives in dry, cloudless air. The radar sees nothing at all. No cloud out the window, no blob on the screen. Often the first warning is the jolt itself, which is exactly why the seatbelt sign stays on in a perfectly blue sky. Now the event everyone remembers. May 21st, 2024. Singapore Airlines Flight 321, London to Singapore, crossing Myanmar at 37,000 feet. And here's the first surprise. It wasn't the invisible kind at all. The final investigation found the aircraft was over thunderstorm cells building fast beneath it, weather the onboard radar simply didn't paint. Investigators couldn't rule out that the radar was under-reading the storm. Crews on 3 nearby aircraft, flying in clear conditions with different radar units, saw the clouds with their own eyes and steered around them. The recorders tell the rest, second by second. 19 seconds of growing shudder. And then, in 0.6 of a second, the vertical force flips from plus 1.35 grams to minus 1.5. Minus G means the floor is accelerating downward faster than gravity can pull you after it. An unbelted person doesn't fall. The airplane drops away, and the ceiling comes to them. And here's the number that should reframe every headline you've read. The altitude changed by 178 feet, not thousands of feet, 54 meters. The violence you feel isn't the distance the airplane moves. It's the acceleration, how sharply the motion reverses. A small drop, reversed hard, throws a human like a rag doll. On that flight, 79 people were hurt, and one passenger died, a suspected heart attack during the encounter. The injuries came from people and objects meeting the cabin. And the aircraft? Structurally fine. It flew on and landed in Bangkok, which leaves the real question, how much can the sky throw at a wing? To answer that, step into a Boeing test hangar in 1995, where engineers are about to destroy a brand new 777 wing on purpose. Every airliner design must pass this. First, engineers compute the limit load, the single worst force the wing should ever meet in a lifetime of flying. Worst gust, worst maneuver, worst day. The wing has to take that limit load without permanent damage. Bend, yes. Break, never. And certification doesn't stop there. The rule, written into federal law, says, now multiply the worst day by 1.5. The structure must carry 150% of limit load and hold it for seconds without failing. So they bend the wing. Hydraulic jacks haul the wingtips upward, meter after meter, past anything the sky has ever done to an airliner. The 777's wing finally let go at 154% of limit load, half again beyond the worst day it was designed to ever see. When Boeing ran the same test on the 787, the wingtips flexed upward roughly 25 feet, 7.5 meters of bend, and the wing held. That is the wall standing between you and the weather. For turbulence to break a modern wing, it would have to beat the worst load ever expected, and then beat it again by half. Could turbulence sneak past that margin? The certification rules thought of that too. The gust requirement writes the ambush into the design. The structure must survive sudden vertical gusts, at their worst near sea level, 56 feet per second of rising air, striking at speed. And the 1.5 factor sits on top of that. A real wing also has physics on its side. A big jet is heavy for its wing size, and the heavier the loading, the less a gust can shove it around. That's why the airliner shrugs through air that tosses a light aircraft. Pilots stack the deck further. In rough air, they slow to turbulence-penetration speed because gust loads shrink as you slow down. Less speed, less force from every eddy. Be careful with the comparison everyone wants to make here. A G number from the cabin doesn't map straight onto one limit line. The rules carve separate envelopes for maneuvering and for gusts, for pushing up and for dropping away, each with its own margin and the same factor on top. So the honest yardstick is the one you already watched, an airframe that took the deadliest encounter in years and flew on, built to a standard where the wing doesn't let go until half again past its worst design day. There's one more piece, and you can watch it from a window seat. The wing is supposed to bend. A rigid wing would fight every gust head-on, hammering each slam straight into the structure and the cabin, and it would have to be enormously heavier to survive its own stiffness. A flexible wing works like a spring. It soaks up the gust, bends, and returns the energy smoothly, the way a tree rides out a storm that snaps a fence post. Modern jets even fight back actively. The 787 senses gusts with accelerometers and flicks its control surfaces automatically, faster than any pilot could, to smooth the ride and trim the loads. So the flexing that frightens passengers is the system working. A wing that never moved would be the one to worry about. Honesty requires one dark chapter because turbulence has destroyed a jetliner. Once, and the case is still taught today. March 5th, 1966. A Boeing 707 leaves Tokyo on a crystal clear afternoon and detours to give passengers a sightseeing pass of Mount Fuji. The mountain was making its own weather that day. Ferocious lee waves, wind slamming over the summit and breaking like surf downwind, with violent rotors spinning beneath. Flying low and close, the aircraft met a gust the investigation called considerably in excess of the design limit. The tail failed first, and the aircraft broke apart. 124 people died. That was BOAC Flight 911, and it stands nearly alone in the jet age. In the 6 decades since, no modern jet airliner has been torn apart by turbulence and cruise. Not because the sky got gentler, because the system learned. Mountain wave forecasts, routing rules, and the exact certification margins you just watched being tested to destruction. So if the airframe is safe, Where do all the injuries come from? From inside the cabin. And the statistics are blunt. Turbulence is the leading cause of serious injuries on airliners. And of the people seriously hurt, roughly 4 out of 5 are crew. That ratio is the whole story. Flight attendants get hurt most because they're the ones standing, working the aisle when the sky lets go. In a -G event, an unbelted human becomes the moving part. Carts, laptops, people, everything unattached keeps going up as the airframe drops away. A lap belt, even worn loose, changes everything. It keeps you coupled to a machine that's engineered for far more than the sky is delivering. The most protective device on that aircraft isn't buried in the wing. It's the strap you were asked to keep fastened. One more thing is true. The bumps are getting worse. A warming climate strengthens the wind shear inside the jet streams, and shear is what breeds clear air turbulence. Researchers at the University of Reading measured it. Severe clear air turbulence over the North Atlantic increased by about 55% between 1979 and 2020. And their projections say more is coming as the world warms. More of exactly the kind radar can't see. But the counter-move is already flying. Aircraft now measure the churn as they pass through it and share it. Thousands of jets feeding live turbulence reports into a shared map within seconds. Pilots increasingly see rough air the way you see traffic on a map app, reported by the vehicles just ahead. The sky isn't getting smoother, but it's getting much harder to be surprised by. So, can turbulence bring down a plane? It did once, in 1966, and engineering has spent the 60 years since building the answer into every wing. Next time the cabin shudders, run the numbers you now know. The worst event in modern memory swung the cabin between roughly -1.5 and +1.8 grams, and moved the jet 54 meters. The wing over your head was bent half again past its worst imagined day, before the design was allowed to carry you. The airplane is not the vulnerable part of the equation. You are, exactly as far as you are unbelted. So click the belt, watch the wing flex, and take the strange comfort in it. Every bend is the design keeping its promise. If hidden engineering like this is your thing, subscribe to Beneath the Wires for more of the machinery quietly holding your world steady.